everyone, this is our STEM engagement presentation. We're Team NASA Student Launch, Team LALC, and we're from Young Engineers in Action. So a brief overview about our presentation today. First, we're going to cover our team structure, then a brief history of NASA and rockets, then rocket components, rocket building steps, when rocketry meets biology and our team's rocket, then practice questions and a Kahoot, and then it's a Q&A session. So first of all, about our team. We are a team of high school students from California. Our team name is LALC NASA Student Launch Team. Our organization name is Young Engineers in Action. And for our team structure, our captain is Catherine Liu, who is in 12th grade from Oxford Academy. I'm Emily Wren, the Chief Operating Officer. I'm a 10th grader from Diamond Bar High. And our Chief Safety Officer is Lee Marquez, a 9th grader at the California Academy of Mathematics and Science. Our TARC officer is Neil Marquez, who is a 9th grader at the California Academy of Mathematics and Science. Rohan Nair is our STEM engagement officer, an 11th grader at Cypress High School. Andrew Liu is our outreach officer, a 9th grader at Oxford, and Jessica Lee is our finance officer, a 10th grader from Oxford Academy. And for our social media, you can find us at our Facebook, Instagram, Twitter, LinkedIn, and website. Now let's talk about a brief history of NASA and rockets. So NASA stands for the National Aeronautics and Space Administration. It was started on October 1st, 1958 as a part of the US government. NASA is in charge of the US science and technology that has to do with airplanes or space. And the NASA Student Launch Program is a 9-month research and competition program.
Student Launch engages students from middle schools to universities in a 9-month engineering design life cycle program, mirroring the activities of a spaceflight program. Teams design, build, test, and launch high-powered rockets and scientific payloads. Teams are divided into 2 primary divisions, college, university, or USLI, and middle school, high school, or SLI. A rigorous and competitive proposal selection process kicks off this Artemis Student Challenge. Once selected, competing teams must complete a series of milestone reviews mirroring the NASA engineering design lifecycle. Each review involves preparing a technical report detailing launch vehicle and payload design, technical drawings, simulation data, safety and hazards analysis, test data, timeline and budget estimations, and STEM engagement. Teams present each milestone via video teleconference to a review panel comprised of NASA subject matter experts. To finish out the season in April, teams compete in a final competition launch event hosted in Rocket City, Huntsville, Alabama, home of NASA's Marshall Space Flight Center.
A brief history of rocketry. In 1232, fire arrows were used by the Chinese. In 1591, the first multi-stage rocket was launched by German fireworks maker Johann Schmidlapp. In 1687, Newton's laws of motion were published. In 1844, spin stabilization was invented, and in 1898, space exploration was proposed. 1926, a successful liquid propellant rocket was launched by American Robert H. Goddard. In 1942, V-2 rockets by German engineers led by Wernher von Braun were launched. In 1946, the first atmospheric testing by the US was conducted. In the 1950s, the intercontinental ballistic missiles were fired. And in 1957, the first satellite, Sputnik 1, was launched. Now let's talk about the components of a rocket.
So the basic outside structure for our TARC rockets includes nose cone, upper body tube, lower body tube, fins, and then the motor containment or motor mount. And the inside structure is in the upper tube, we have an egg and altimeter. This year it's 2 eggs, and the under tube is going to have a parachute and a rocket motor, which is secured by the motor mount. The outside components are made of these body tubes. These ones are made of cardboard, and they hold the inner parts together during the launch. It's important to cut the tubes to the correct length so the rockets can be stable as tested on open rocket software or other softwares. The nose cone is to reduce the drag on the rocket, and we use parabolic, I think, and there's parabolic, ogive, blunt, and hemispherical. There's also other nose cones that people have experimented with, and we use a plastic 3D printed nose cone. The purpose of the transition piece is to help the two tubes of the rocket transition and separate during launch. And we use cardboard for our transition pieces. The bulkheads are connected to the transition pieces and also connected to the parachute. So when the separation occurs, there is a parachute to help prevent the rocket from falling too fast. The fins are to maintain rocket stability. Without them, the rocket would just like spin out of control. So you need to use them. And there are two fins, which we use on our TARC rocket. And there's also these other fins, delta fins, which are, these ones are made of wood. And we have a motor mount. This is important because it holds the motor and secures it so the rocket can fly. And if the motor falls out, it's very dangerous. So you don't want that to happen. Now, our recovery system is one parachute, and the importance of a recovery system is so you can reuse the rocket and recover it after it's landed. Otherwise, it would just explode on impact. And on larger rockets, there may be tracking systems because they may glide farther than expected. Our payload has 2 eggs and an altimeter so we can record flight data. Otherwise, we would not know how high the rocket went. Now, these are the basic rocket building steps. These are the basic rocket. Okay, so the steps are to cut both body tubes to desired lengths, cut tube fins to their desired lengths, glue the transition pieces and the bulkhead, 3D design the motor mount, and that can be attached. Add in rail buttons or launch guides. Secure the tube fins to the bottom tube. Drill holes for the nose cone and altimeter. Make a case for the egg so it'll stay safe. Add a recovery system, parachutes, and spray paint the rocket for extra thickness. For the first step, to cut both body tubes to the desired lengths, we use hand saws, or we can use knives or X-Acto blades. And we use a box that has a V-shaped cut into it to hold the tubes in place while we're cutting them. For the second step, cut tube fins. We usually use 3, but 6 as pictured in this rocket, we also use that. And the most important thing is that the fins need to be spaced evenly. And for the 6-finned rocket, we don't need to think about that because it'll just fit perfectly. And delta fins will be, can be also used, like we use delta fins on our NASA student launch rocket. So for step 3, we glue the transition piece and the bulkhead. So we pop out the bulkhead centering rings and from the plywood that is laser cutted, we get the screw eye and twist it into the bulkhead. And when we put it mostly all the way in, we will glue it with epoxy, and this will secure it permanently to the bulkhead. And we will epoxy the bulkhead to the smaller tube, the top tube, and we will also glue the centering rings on the outside of that tube. And we will wait for 1 day for the epoxy to dry. For the motor mount, we use 3D CAD to design the motor mounts. This is one that is not 3D printed. It's wood with the centering ring inside, or the motor mount ring inside. And this is hard to build, so we just 3D print them. For step 5, we drill holes on the bottom tube and we put motor rail buttons or launch guides into the holes. For step 6, we secure the tube fins. We mark holes on the tube fins and the bottom tube, and we're going to drill holes in the bottom tube and the tube fins, and we screw them in and we epoxy the fins to keep them in permanently. For step 7, we drill holes for the nose cone and for the altimeter. So we have a 3D printed nose cone. So there are 2 holes on each side. So we just drill holes, make sure they're aligned with the nose cone. And we also drill holes in the top tube so that the altimeter can read the pressure correctly. For step 8, we need to make a case for the egg. We use foam from a memory foam pillow, or we use foam from pool noodles, and both these are good options. We take measurement of the egg and we cut the foam into a shape of an egg so that the egg can be inside the foam, and we test if it's good or not. Step 8, we add a recovery system. We use Kevlar rope, blast protector, and parachutes. The blast protector is so that during the blast, the blast won't burn a hole through the parachute or burn the rope of the parachute. This way, the rocket can come down safely every time. And we have 2 parachutes, one for the bottom, one attached to the bottom and one attached to the top. And we tie rope around the motor mount, and we tie the blast protector away from the parachute, and then we tie another rope to the end of the bulkhead, and another parachute. For step 10, the last step, we spray paint the rocket, and we usually just spray paint it one solid color, but designs can be added if you want.
When rocketry meets biology, our team's rocket. So here's an overview of the dimensions for our NASA student launch rocket. The length is 183 centimeters, weight is approximately 16 pounds. Apogee, or the highest height that it flies, is 4,501 feet. 1 feet. The maximum velocity is 525 feet per second, and maximum acceleration is 241.5 feet per second squared. And our thrust to weight ratio is 5.7 to 1. The length distribution, the nose cone is 58.4 centimeters, body section 1, 40.6 centimeters, body section 2, 83.8 centimeters, and the total drift of the rocket with 20 miles per hour wind is approximately 2,091 feet. The materials we used for our rocket, the main body, nose cone, fins were all made out of fiberglass. The streamer and parachute were ripstop nylon, and the glue was epoxy glue. And we decided on fiberglass because it's highly durable and resistant to most forms of moisture and corrosion. And it's also a good compromise between weight and strength. And we used ripstop nylon for the streamer and parachute because it's durable and doesn't break easily. And we didn't consider other options due to convenience of purchasing. For our rocket recovery system, at apogee, the streamer is deployed from the bottom compartment, and it will be 6 inches by 30 feet. And at 600 feet, the 72-inch diameter parachute will be deployed from the first compartment. And both recovery systems use black powder ejection, which is connected to an altimeter in the avionics compartment in between the two rocket body tubes. And for our subscale flight results, we had a successful flight to 2,193 feet with successful deployment of the streamer at apogee and parachute at 600 feet. We also performed a successful ground test prior to launch. And we also changed the location of one black powder for the streamer to come out more easily. For our payload, the purpose is to conduct an experiment on how forces and altitude affect mimosa pudica plants. The tumbler was designed to prevent plants from turning upside down, and the 3D printed capsule is replicable. And for our mimosa pudica plants, there are 3 inside the rocket as our experimental group and 3 on the ground level as the control group. And we're going to have 2 cameras inside the tumbler in order to document the process of the opening and closing behavior of the plant's leaves. And we installed lights inside the tumbler to ensure that each plant receives the same amount of light. For our tumbler design, it's designed so that the plants can always stay upright, and our tumbler is sphere-shaped, and a weight is to be placed at the bottom, and the tumbler is easily removable from the rocket tube after the launch. For our mimosa pudica plants, we conducted extensive research on the biological properties of mimosa plants and previous experiments conducted on them. So by preliminary research, our team found out that the earliest related experiment was conducted by a scientist named Prefer in 1873, and that experiment showed that repeated mechanical stimulation of mimosa leaflets led to a decrease in its sensitivity. And 2 of the recent related experiments used the leaflet closure as a dependent variable and explored the vertical dropping light intensity and other factors as the independent variables. Some other recent research on mimosa plants focused on the cellular level instead of the behavioral level of biological properties and the learning behavior of mimosa plants. But based on our team's preliminary research, it seems that none of the previous experiments about plant cognition on mimosa plants were conducted in flying rockets, and all of the previous experiments were conducted in a lab on the ground level. And our team is curious to see how different forces and altitude, which are the independent variables, would affect the leaflet closure behavior, which is the dependent variable in flying rockets. And our team thought it would be interesting to explore how rocketry, space engineering, biology, psychology, and cognitive science would interact with each other in our team's experiment. So our team purchased and observed mimosa pudica plants, and we found out that they're extremely sensitive to temperature and light. And our team will grow mimosa pudica plants seeds at the right time so that the plant size can be controlled. There will be 3 plants inside the rocket as the experimental group and 3 on the ground level as the control group. For the cameras and light, we will use two MateCam 32 gigabytes 808 keychain cameras to document the plant inside the rocket. And this camera is a 120-degree wide-angle motion activated portable pocket camera. And this keychain camera is often used in model rocketry due to its small size, and we'll also use LED lights to make a clearer picture.
The 3D design of the payload can be replicated easily if it breaks or if we just need to redesign it. And we can easily observe the changes between the tested groups and the control group on the ground because of the simplicity of reproducing the capsule. And after the launch, we're going to see if there's correlation between the rocket forces and the altitude to the mimosa plants and their opening and closing behavior. We're going to see if habituation occurred, which is a behavior that repeated exposure may lead to decrease in response strength. And we're going to see if our hypothesis of our experiment is correct. This chart here is a risk mitigation chart. It shows how severe and how likely an event is, and event like launch checklists include recovery preparation checklist, payload preparation checklist, electronics preparation checklist, motor preparation checklist, rocket preparation checklist, launch pad setup checklist, and a post-flight checklist.
These are a few practice questions. What are the main components for the basic outside structure used in our TARC rocket? We have the fins, the bottom body tube, the top body tube. We have the nose cone. What does NASA stand for? NASA stands for the National Aeronautics and Space Administration. And what type of fins are used on the rocket? We use tube fins for our rocket.
Now it's time for our video and a Q&A session. So we produced an 8-minute video about our Subscale rocket launch at the Friends of Amateur Rocketry facility at Mojave Desert on January 1st of this year. And this is the YouTube link. So we will watch our video now.
We need a video tape in this case. And we have phone just a video tape.
I'm ready anytime you're ready. Or do you want a countdown or something?
Okay. Range is clear. Sky is clear. 5, 4, 3, 2, 1.
Okay, this is why we do ground tests. second, then get position. Get a safe distance.
Range is clear. Sky is clear. 5, 4, 3, 2, 1.
Okay, we're NASA student launch. We're going to launch this in 5, 4, 3, 2, 1. Okay, nice launch up. Waiting for deployment.
Thank you guys for watching, and if you have any questions, feel free to contact us on our social media, our Facebook, Instagram, Twitter, LinkedIn, and website. Thank you guys for watching.
If you would like to learn more about NASA Student Launch or other NASA Artemis student challenges, visit us at our website or on social media.